Hola, ¿qué está pasando, amigos? Welcome back. We're in step 9, in which we're going to identify the essential nodes, non-essential nodes, and supernodes of our circuit. Remember that in step 8, we combined the three types of grounded circuit equations: the grounded KVLs, the branch constitutive relations, and the grounded KCLs to form the matrix equation AR transpose times G times AR times the unknown vector of grounded node voltage potentials, so all node voltage potentials minus the ground node. Then we had an extra term having to do with currents running through the voltage sources along with the voltage source incidence matrix of the grounded incidence matrix. And on the right-hand side, we have this constant forcing term. Remember, because we knew the currents running through the current sources, this showed up as if it was a forcing term, hearkening back to the ideas from an ordinary differential equation class. Now, most electrical engineers say we can't do much more than this, go back to modified nodal analysis and be done with it, because this voltage source term shows up in this equation and we don't actually know the currents running through the voltage sources. But one of the claims that I make is we actually know information about this vector based on linear algebraic structures in such a way that we can eliminate this term by multiplying by the appropriate vectors to turn that matrix to zero. Let me be more specific about that. Remember that when we looked at the node voltage potential vector that included everything and the ground node, that's why G shows up, that vector shows up in a general linear systems problem with a known right-hand side vector, which is the voltage source KVLs. Now, when we looked at solving that general linear systems problem using linear algebraic structure, we said that every vector that solves that thing is going to look like a particular solution plus a linear combination of special trivial solutions that are linearly independent. If you want more about this, go watch the 3 videos from step 6, the step 6 itself, and then the 2 extension videos. We go into really great detail about how this works. However, what that means is that the vector U sub 0, which was the grounding matrix transpose times the original node potential vector, including ground node, that matrix includes specific information about voltage source redundancies. We can say that in a different way, which is when we look at that vector contains interdependent entries where some of the entries of this vector are related to other entries in this vector by known constants, which are the values of the voltage sources in the circuit. Just like we spoke about in step 6, perhaps we can eliminate some of those dependencies between the individual entries of U sub 0 and get down to a minimal set of node voltage potentials that govern the entire behavior of our circuit. Specifically, if you remember in step 6, we did all of the analysis of the types of independent node voltage potentials that came up with reference only to the voltage sources. In step 7, we talked about how we could eliminate a ground node. In other words, we could get rid of one independent voltage potential because we could set the ground node to 0. What we haven't done is figured out how step 6 and step 7 can be combined to get down to that minimal set of node voltage potentials from which all other circuit variables can be calculated. With that in mind, we're going to refine the definitions that we gave in step 6 to incorporate the information that occurs when I ground my circuit. Remember, the whole idea of step 6 was to identify generalized nodes and ordinary nodes. Generalized nodes are any collection of nodes which are connected by paths of voltage sources. In other words, any collection of node voltage potentials that have dependencies amongst them. Ordinary nodes are nodes to which no voltage source is connected. In other words, those are independent node variables. They do not relate to any of the other entries in that node potential vector. The whole point of this classification was to figure out how many variables we could eliminate based on the interdependencies of the voltage sources. But we also now introduce the idea of grounding. Specifically, we're going to define the ground node to be the node that we set to the ground reference. In this case, we've chosen node 7 to be that situation, and the corresponding node variable that we had was u sub 7, we claim that in ground node, that node variable was not unknown, but instead node, and we set it equal to 0. Once we've established our ground node, we might want to look back at the concept of a generalized node and realize that if our ground node shows up in a generalized node, all other node variables in that node are immediately known because they're connected to ground through voltage sources. Ground has potential 0. Voltage sources have known values. We can reverse engineer the values of those other node voltage potentials by combining that information. Those type of nodes we're going to call non-essential nodes. In other words, a non-essential node is any node in a generalized node in which we've chosen ground. Or if we choose ground within a generalized node, which we've done here, in this case, U2 is a non-essential node. In fact, not only is it non-essential, but we know U7 is 0. We go from U7 to U2 in the positive direction. U2, the value of that thing must be the constant V sub V1. In this case, V sub V1 is 5, but in general, it's anything that the engineers that design the circuit want it to be. With that, we've eliminated two variables by combining the ground information with the generalized node information. Next, we define the sister concept of non-essential nodes to be essential nodes. We say that as an essential node is any ordinary non-ground node in our circuit. Remember that in step 6, we had ordinary nodes 1, 3, and 6. And in this case, our essential nodes, none of those are grounded, are going to be 1, 3, and 6, and each of those are going to be independent, necessary node potentials that we need to calculate. Let's go ahead and write those in red. With this, we've almost finished our refinement of node classification based on choosing ground. We said that the ground node was our chosen datum node. We said that non-essential nodes were any nodes connected to ground via voltage sources. In other words, any other nodes in a generalized node in which a ground node sits. Essential nodes were ordinary nodes that were not chosen as the ground node. The last category of nodes that we're going to use to get rid of the redundancies is called a supernode. A supernode is any generalized node in our circuit that does not contain the ground node. So in this situation, we said that generalized node 1 contained the ground node. That can't be a supernode. But generalized node 2 did not contain the ground node. And thus we said that the first supernode in this circuit is the one containing nodes 4 and 5. Remember that for each generalized node, we had at most one independent node potential variable. We chose in step 6 to set that independent variable to be U4. Once we had U4, we could calculate U5 by recognizing that U5 is U4 minus the value of voltage source 2. Because each supernode comes from a generalized node, this circuit had two generalized nodes. It could have at most two supernodes, but generalized nodes only become supernodes if they do not include ground. The first generalized node includes ground, so it is not a supernode. In other words, we only have one supernode in this circuit. Moreover, we have now just specified the independent entries of the node potential vector that completely classify our circuit. Those are U1, U3, U6, and U4. The claim is if I get those 4 node voltage potentials, all other information in my circuit come from those 4. With this, what we've done in step 9 is to make very explicit the node potential variables that we're going to eliminate based either on connectivity of voltage sources or grounding. In this situation, we've eliminated 1, 2, 3 variables. We had 7 total. We have 4 independent variables that we must calculate in order to classify the behavior of the entire circuit. In step 10 of this algorithm, we're going to combine the intuitions from the extensions of step 6 to figure out how to use this information to reduce this vector and turn this thing into a non-singular linear system problem involving a positive definite matrix. This is a classic well-known form of a linear system problem that shows up in many STEM fields. If you want to know more about this, see me in step 10.